Hello engineers, and welcome to 3.2.2, which is pneumatic power. We're going to talk today about pneumatics, how they work, how to calculate all sorts of things about them. Let's get started. Pneumatics is the use of a gas flowing under pressure to transmit power from one place to another. It doesn't use a liquid like hydraulics. Pneumatics specifically use a gas. Many times it's just air. Using atmospheric air, they pressurize it and push it through a system. Pneumatic systems use a gas. They're quicker. One of the pros is that they're really, really fast. They're quicker and jumpier in their motion. They are not as precise. So they go from 0 to all the way extended. You can't really, it's hard to really get them because the gas is compressible. It requires a lubricant. A lot of times that lubricant is pushed in through the gas itself, so it can require a lubricant. They're generally cleaner. The hydraulic fluid can get over all sorts of stuff. So if you need, like in food applications, pneumatics are generally used because they are cleaner in that way. They operate around 100 psi. So, and they generally produce less power in general. You can get a lot of power out of them, but you're operating at much higher pressures in that case. Early pneumatic uses, a bellows, blacksmiths use these things to push air. You squeezed it, air entrance, so the valve would suck it in. Maybe you have a fireplace at home. We had one as I did as a child, and I would always use the bellows to get that fire going. Otto van Gerke, he took two hemispheres and then you pump the air out. So it's a negative pressure. So a lot of people say it sucks them together. No. The pressure of the air around the atmosphere would push them and hold them together when you pull the air out. America's first subway used pneumatics. There are a couple things that affect gases. They're affected by 3 different variables, and you probably learned this in chemistry if you've gone through chemistry. It's the temperature, the pressure, and the volume. So if you affect any one of these things, you're going to affect the other 2. So if you increase the temperature, the pressure and volume will change. Or if you keep the volume constant and so this is, I think, Boyle's law, they call that inside of chemistry. There's a couple different types of pressure. The first one is gauge pressure. For instance, if I look on a pressure gauge for my tires, my tires say that they're pumped up to 25 psi. There's 25 psi in the tire, but then there's also atmospheric pressure outside, so it's not accounting for atmospheric. Atmospheric pressure is generally 14.7 psi. Maybe you've heard of like the air pressure, the barometer is going up or down. So it's right around 14.7. So even though my truck says 20 psi, it's really 34.7. That's the absolute pressure. So absolute pressure is the total pressure of the air pressure plus the gauge pressure. So right now, you're sitting, watching this video. There is 14.7 pounds on every square inch of you right now. You can't feel it. You've grown up with it. We've evolved to accept it. But maybe you've gone down in the water and you feel your ears pop, or you go up in an airplane and you feel like that pressure, that difference can affect you. And you can feel when it changes. But there is pressure on you, and the absolute pressure is the gauge pressure plus the atmospheric pressure is equal to the absolute pressure. Absolute pressure, they measured in PSI, newtons per square meter if it was in metric system. Standard atmospheric pressure equals 14.7 PSI. If a gauge reads 120, what is the absolute pressure? The absolute pressure is going to be 134.7. That's going to be the absolute pressure. You just add 14.7 to it. Absolute temperature. If you've been through physics, absolute temperature is a little bit tricky. Absolute zero is negative 460 degrees Fahrenheit, or 0 Kelvin, or negative 273 degrees Celsius, or there's another, it's called 0 Rankine. These are different. Fahrenheit is to Rankine as Celsius is to Kelvin, if that makes any sense to you. So with Rankine, this is what we're going to use. Degrees Rankine is equal to whatever your degrees in Fahrenheit is, plus 460 degrees. So it says if the temperature in a system was 65, what's the absolute temperature? You're going to take Fahrenheit and you're going to add 460 to it, so it's going to be 525 degrees Rankine. Pascal's law. Pressure exerted by a confined fluid acts on all directions. The force per unit area is on a surface. We've got a couple of different terms. P stands for pressure, and it's pounds per square inch. Force is in pounds, and area is in inches squared. So it says how much pressure can be produced with a 3-inch diameter. So this is 3 inches here, from here to here, and 50 pounds of force. So pressure is equal to your force divided by your area. My force is 50 pounds, and my area, it's a circle. So I have to find the area of a circle, and the area of a circle is 2 pi times the radius. And that's going to 2 pi r. No, it's pi r squared. Take that back. Area of a circle equals pi r squared. So pi times 1.5 squared. And if you do that, and this is inches again, so 50 divided by all that, it turns out to be 7.0 pounds per square inch. Or you can write PSI. So that's how much pressure. Pressure is in PSI. Next one, how much pressure, we did that one. The perfect gas laws describe the behavior of a pneumatic system. Boyle's law, the volume of a gas at a constant temperature varies inversely with the pressure. So this is talking about volume and pressure. So they're keeping the temperature constant, meaning this: if you have a bigger volume, that means that your pressure goes down. That's what that means by inverse. So if you have a volume of gas and you squeeze it, the pressure is going to go up. So volume is going to go down. That means the pressure goes up. Those are inversely related. That's Boyle's law. It says a cylinder is filled with 40 cubic inches of air at 60 psi, and then the cylinder is compressed to 10 cubic inches. What is the resulting absolute pressure? So I think that law was P1 V1 equals P2 V2. P1 V1 equals P2 V2. This is Boyle's law. So I'm going to put that into use over here. P1 V1 equals P2 V2. You got to be careful because you have to use absolute pressure when you're doing all these problems, so it becomes a little bit tricky. 60 psi, so you got to change that into absolute pressure, so that's going to be 74.7, and the volume was 40. Pressure 2, what is the resulting absolute pressure? So we don't know the pressure, but now the volume is 10. So you divide this side by 10, and that P2 is going to be equal to, turns out to be 300 psi. Taking 74.7 times 40 divided by 10 ends up equaling 300. Just watch out. Your pressure always has to be an absolute pressure. Charles' law, it says that the volume of gas increases or decreases as the temperature, provided the amount of gas and pressure. So if we keep the pressure constant, so if you heat up a gas, it's going to get bigger. And if you cool down a gas, it's going to get smaller. That's what Charles' law is stating. Charles' law says this: V1 over T1 equals V2 over T2. Be careful that you have to have your temperatures in absolute temperatures as well. So you got to add 460 to it if you're using the Fahrenheit scale. Let's apply it here. So V1 over T1 equals V2 over T2. So expandable container is filled with 28 cubic inches. So that's my initial volume. So 28 for V1. And it's sitting, it's 32 degrees Fahrenheit. So there's temperature 1, but I got to add 460 to it. So 492. The container is removed and it's heated. What's the result? So we don't know the volume, and you're heating it to 200 Fahrenheit. So that's going to go down here for T2. Got to add 460 to it. 660. Now to solve this problem, I'm going to cross multiply. So 660 times 28, and then I'm going to divide by 492. And I end up with my volume equal to, let's see, I may have to, that turns out to be 38. Now it's 38 cubic inches. And it's heating it, so it should get bigger. So it started out at 28, and that makes sense that it gets larger. So in my brain, that kind of makes sense of that I'm getting a number that I think is probably the right number. Another Charles law. Oh, this is the same thing. What is the? Yeah, this is the end. This is the same one. Gay-Lussac law. The Gay-Lussac law. It says absolute pressure increases or decreases as the temperature, provided the volume is constant. So if you keep the volume the same and you heat it up, when you heat it up, the pressure is going to go up. So that is saying, putting it in math, P1 over T1 is equal to P2 over T2. And this, again, this needs to be absolute pressure, and this needs to be absolute temperature. So in both of these cases, you're going to have to change the temperature to absolute temperature and the pressure to absolute pressure. Let's see how we would do that in a problem. A 300 cubic inch sealed air tank is sitting outside in the morning. Temperature, the tank is this. The pressure gauge reads 120. By afternoon, the temperature inside the tank is expected to be close to 90. What is the absolute pressure at that point? So, we're looking for the pressure. So this is going to be an application of the Gay-Lussac law where it's P1 over over T1 equals P2 over T2. So what's my initial pressure? 120. And it's gauge, so we have to add 14.7. So 134.7. That's my initial pressure. And the temperature outside is 62 degrees Fahrenheit. We got to add 460 to that. So 522. What pressure is it expected, right? So we're looking for this. We don't know. Pressure 2. But we know the temperature is 90. So that goes over there. So I got to add 460 to it. That's 540. So doing a little bit of math, where I'm going to cross multiply 540 times this, divided by 522. Pressure number 2 turns out to be 139 psi. Now that's absolute, the absolute pressure on it. If you wanted to know what the pressure, the pressure on the gauge would say, you'd subtract 14.7 and it's like 124. So this tank, it says 120, it's going to go up 4 psi basically throughout the day. So that's that looking at that needle, it's going to raise 4 psi throughout the day. Common pneumatic system components. You've got all sorts of fun things in here. You got a tank where you store all your air. You've got lines. They can be flexible, they can be rigid, they can be made of all sorts of different materials. There's a compressor, something to take the atmospheric air and squeeze it down. You've got some cylinder at the very end of the line where you're pushing, opening. Filters. So any particulate matters that are going through, you can filter those out. A regulator that tells you how much pressure you're allowing to go to your cylinders. A drain valve, because a lot of times when you squeeze the air, you're going to have water come out of it because if there's sometimes they have dryers in line of these things that take the water out of it. So these things, you can open this up and you can let the water drip out of them. And at the bottom of your tanks, there's always some way to let the water out as well. A valve that, kind of like in hydraulics, that let the air in and stop the air. A pressure relief valve. If the pressure gets too high, there's a spring that doesn't allow the system to blow up. Different types of compressors. There's pistons. I think that's the typical compressor that a lot of you maybe have. If you have an air compressor at home, you hear that roar. They have ones that are rotary screw. So this is a supercharger. If you've ever heard of a turbocharger or a supercharger on a car, this is a rotary screw compressor. Maybe you've seen like the septic sucking places that come out and suck the nastiness out of your tank. They use a rotary screw compressor on the top of their actual tank to suck air out, which is pulling that material into their truck. So they use these rotary screws. These are we have a place, Hi-Pro, in Platteville. This is what they machine. They machine these for a lot of different places in the world that make these rotary. It's pretty tough to machine those. They do some really cool stuff. A rotary valve, so there's something going in a circle, pulling that air in. Yeah, maybe you've heard of Elon Musk's Hyperloop, pulling all of the air out of a tube and then sending somebody through it, like to go, like imagine a subway with no air resistance on a maglev train. You could really go from like, I don't know, New York to LA, a couple hours rather than what it is today. All right, well, thanks a lot, guys. Talk to you later.